Hey there, and welcome to part 2 of Graph Theory with Python. My name is David Amos, and in this video, I'm going to show you how to represent graph data structures using the Python programming language. If you haven't already seen my video on the origins of graph theory, I'll put a link to it right up here. Before I show you how to represent a graph data structure in Python, I need to talk a little bit about the precise definition of a graph. In mathematics, a graph, which we'll denote with a capital letter G, is a pair of two sets, V and E. The set V is called the vertex set, and the set E is called the edge set. Now, if you don't know what a set is, you can think of it as a collection of distinct objects. Although you'll see in a little bit that we're going to use this a little bit loosely. We can actually, in some cases, have multiple objects in a set. If you're interested, I have a video on some of the weird things that can happen when you aren't careful about how you define a set. I'll put a link on the screen and also down in the description. For our purposes, though, we're just going to think of the sets V and E as collections of objects. Now, the vertices of a graph can be any object we want. They could be people in a social network. They could be items manufactured by a company. They could be mathematical objects like functions, or they could be Python objects like integers or strings. In the vast majority of the examples we'll look at, we're going to take our vertices from the natural numbers, including 0. So for example, we could have a graph with a vertex set containing the numbers 0, 1, 2, and 3. The edge set of a graph is a collection of pairs of vertices. For example, we could have an edge set with the pairs 0, 1, 0, 2, 1, 3, and 2, 3. Now, from a mathematical standpoint, this is all a graph is, a vertex set and an edge set. That's not very intuitive though, and we often represent graphs graphically using dots for the vertices and lines connecting the dots to represent edges. Let's draw the graph represented by our vertex set V and edge set E that we have here. We have 4 vertices, and I'll go ahead and label them 0, 1, 2, and 3. We also have 4 edges. We have the edge 0, 1, which I can draw by connecting vertex 0 to vertex 1. We have the edge 0, 2, which I can draw by connecting the vertex 0 to the vertex 2. The edge 1, 3, which is this edge, and the edge 2, 3, which is this edge here. It's important to remember that the way that a graph is drawn doesn't influence the nature of the graph itself. What I mean by that is I could draw the graph this way. I could label this vertex 0, this vertex 1, this vertex 2, and this vertex 3. Now when I draw my 4 edges, there's the edge 0, 1, the edge 0, 2, the edge 1, 3, and the edge 2, 3. I've drawn this graph in such a way that the lines do not cross here in the center like they did in the first drawing, but it is still the same graph. I could even get a little crazier if I wanted to. For example, I could draw the 4 vertices in a straight line. Here's 0, 1, 2, 3, and draw my edges like this. Here's 0, 1, here's 0, 2, here's 1, 3, here's 2, 3. This is another way to represent the same graph graphically. There are some other things that can happen in graphs, such as 2 vertices having multiple edges between them, and 1 vertex having an edge connected to itself. Let me show you what I mean. Here's a graph representing the 7 bridges of Königsberg from the first video in the series. Let's label the vertices A, B, C, and D. The vertices A and B have 2 edges between them, the same for A and C. A graph with this property is called a multigraph. Let's write out the vertex set V and edge set E for the Königsberg graph. V is the set of the 4 vertices A, B, C, and D. Our edge set E has 7 edges, which if you saw the first video in the series, you'll recognize as the 7 bridges from the city of Königsberg. They are A, B, which can be this edge here, a second edge between A and B, which is this edge, 2 edges between A and C, which gets us these 2 edges here, an edge between B and D, an edge between A and D, and an edge between C and D. This is where we're abusing the notion of a set a little bit. we have two copies of the edge A and B and two copies of the edge AC. Now, in a real set, we couldn't have multiple copies of the same object. A set like this is usually called a multiset. In some cases, a graph can have an edge between a vertex and itself. We call these edges loops. And here's an example of one on this graph. Let's write out the vertex and edge sets for this graph. Our vertex set V, again, has 4 elements, 0, 1, 2, and 3. And our edge set has 6 elements. We have the edge 0, 0, representing the loop, the edge 0, 1, the edge 0, 3, the edge 1, 3, the edge 1, 2, and the edge 2, 3. Now, mathematicians study graphs for lots of reasons. They're incredibly useful as models for relationships between objects. A great example that most people are familiar with is a social network, such as Facebook or LinkedIn. In Facebook, for example, the vertices are the people who are members of Facebook. Edges represent the friendship relation between Facebook friends. Now that you've seen how we represent a graph mathematically, let's take a look at how we can represent this in Python. First, I want to mention a little bit about the version of Python that I'm going to be using and that you should use to follow along successfully. I'm using Python 3.9.1. Most everything that we'll be doing in this video series can be done using Python 3.6 or greater. In a couple of rare instances, it'll be helpful to have Python 3.8 or better. If you need a resource for getting the latest version of Python installed on your system, I highly recommend RealPython's Python installation guide. I'll drop a link to that in the video description. I'm also using Microsoft's Visual Studio Code editor. This is my preferred editor, but by no means do you have to use it in order to follow along. Use the editor you love the most. Now remember that mathematically, a graph is a pair containing a vertex set and an edge set. The notation that mathematicians use to represent this pair looks a lot like a common Python data structure, the tuple. We could use a tuple to represent a graph, but we're going to take it one step further and use something called the named tuple from the collections module. Let me go ahead and import that now. Named tuples are great for creating blueprints that you can use to instantiate new objects. They work a lot like a tuple, except that they allow you to give names to the tuple's components. Once you've created a named tuple, you can use it to create new instances of objects, much the same way you would using a user-defined class. To create our graph type, we start by assigning a named tuple to the named graph with a capital G. The first thing we have to pass to named tuple is a string containing the name of the type, which for us is just graph with a capital G. The next thing you have to pass to named tuple is a string or an iterable containing the field names. Now I prefer to use an iterable like a list with strings containing the field names. These will be the names of the components of the tuple. For graphs, that would be vertices and edges. Mathematicians commonly refer to vertices in graphs. However, computer scientists often prefer the name nodes. They're really the same thing. Nodes is a little bit shorter and easier to write, so I'm going to use that instead of vertices in our graph type. Now that we've created the graph named tuple, we can use it to start instantiating graph objects. Let's create one representing the Königsberg graph that we saw earlier. I'll put that picture side by side with my editor window so we can refer to it while we're instantiating the graph. The Königsberg graph has 4 vertices, A, B, C, and D. We'll use Python strings to represent each node and a list to represent our collection of nodes. We'll assign the list to a variable name called nodes. There are 7 edges in the Königsberg graph. We'll use a tuple to represent each edge and store them in a list assigned to a variable called edges. There are 2 edges between the nodes A and B, this edge and this one. There are also 2 edges between the nodes A and C, this edge and this one. We have 1 edge between the nodes A and D, this edge here. 1 edge between the nodes B and D, this edge here. And 1 edge between the nodes C and D, this edge here. To create a graph object representing the Königsberg graph, we'll pass our nodes list and our edges list to the graph name tuple we created earlier. Let's call it capital G. Now we've created a graph data type based exactly on the mathematical definition of a graph. That's great, but it's not going to be the best way to represent a graph for certain kinds of problems. For example, if you saw my first video in the Graph Theory with Python series, we talked about how Euler solved the problem of whether or not there exists a continuous walk through the city of Königsberg that uses each bridge exactly once. Now, Euler proved that this was impossible, but if we tried to construct such a walk using this graph data type we've defined, we'd have to do a lot of looping over the edges list. This is terribly inefficient. So while this data type is convenient for entering information about a graph, it's not the best representation for actually doing something with a graph. There are two other kinds of representations commonly used in graph algorithms, the adjacency list and the adjacency matrix. Let's take a look at what each of those are. The first representation we'll look at is called the adjacency list. You can think of an adjacency list as a list of lists. Each list in this list of lists represents a single node in the graph, and the list corresponding to each node lists all of the nodes that are adjacent to that node. By adjacent, we mean connected to that node by an edge. So for example, in the Königsberg graph, node A is adjacent to node B 2 times because there are 2 edges connecting A to B. So we'll list it in the adjacency list twice. A is also adjacent to C twice because there are 2 edges connecting A to C. It's also adjacent to node D. Node B is adjacent to A twice because there are 2 edges connecting A and B. And it's also adjacent to node D. Node C is adjacent to A twice and also adjacent to node D. Finally, node D is adjacent to node A, node B, and node C. One thing you can notice about the adjacency list right off the bat is that it doesn't require as many characters to write out as the standard mathematical representation of a graph. That's because we list the node at the beginning and then each node that it's connected to in its adjacency list, without having to repeat that node multiple times for each edge. Also notice that how I've written this is by putting each of the 4 nodes followed by a colon and then a list containing each of the other nodes in the graph that they're adjacent to. It kind of looks like a Python dictionary, and that's not by accident. If we add some curly braces and some square brackets around each list, you get a good idea of how we can represent this using Python. Let's get back to our editor and write a function that takes a graph instantiated using the graph name tuple we defined earlier and returns an adjacency list as a Python dictionary. We're going to write a function that returns the adjacency list representation of a graph, but the word list means something in Python, and it's not the same thing as an adjacency list. As you've seen, we can use a dictionary to represent the adjacency list, so we're going to call our function adjacency dict. This function will take one parameter, a graph. Now all Python functions should have a docstring, so I'm going to go ahead and write one now. The first thing we'll do is create a dictionary that we'll use to hold the adjacency list representation. I'm going to call that dictionary adj for adjacency. The keys of this dictionary are the nodes of the graph, and the values are lists of adjacent nodes. Let's create this using a dictionary comprehension. Each key will be a node, and we'll start each value as an empty list. We need to do this for each node in the graph's node list. Next, we're going to loop over all of the edges in the graph. Let's take the 2 nodes in each edge and assign them to variables called node 1 and node 2. Since there's an edge between node 1 and node 2 is adjacent to node 1, which means we need to append node 2 to node 1's adjacency list. On the other hand, node 1 is adjacent to node 2, so we also need to append node 1 to node 2's adjacency list. When this for loop completes, we'll have a dictionary with one key for each node in the graph and a list containing all the nodes adjacent to each node. That's exactly the adjacency list representation, so we can go ahead and return this dictionary. Let's run our code and see what we get as the adjacency dict for the Konigsberg graph we defined earlier. My code is stored in a file called graph.py. I'm going to run this with the I flag, or interactive flag. That's going to execute all of the code in graph.py and then drop me into a Python shell where I can interact with everything that's been executed. Now, we created a graph called G representing the Konigsberg graph. Let's take a look at that. It has 4 nodes, A, B, C, and D, and the 7 edges from the Konigsberg graph. Let's pass that to the adjacency dict function. The dictionary returned by adjacency dict has 4 nodes, A, B, C, and D, and lists containing all of the adjacent nodes. If you compare it to the adjacency list we wrote when I told you what an adjacency list is, you'll see they're the same. A is adjacent to B twice, to C twice, and also to node D. B is adjacent to A twice, and also adjacent to node D. C is adjacent to A twice, and also node D. And D is adjacent to nodes A, B, and C. Our adjacency dict function is working beautifully. There's something important we need to talk about though. Using a dictionary to represent the adjacency list representation has an important consequence for nodes in our graph. Nodes are used as dictionary keys, and in order to be a dictionary key, nodes have to be of a hashable type. One of the prerequisites for being hashable is immutability. So for example, things like strings or integers, even tuples are fine, but lists, dictionaries, and most user-defined classes are mutable and therefore not hashable, so they can't be nodes in our graphs. In practice, this might be a pretty severe limitation, but for our purposes, we're just trying to learn some graph theory. We're going to use integers and strings for nodes in all of our graphs, which means we won't run into any problems when calling our adjacency dict function. The adjacency matrix represents a graph as a matrix, or a two-dimensional array. Each row and column of the matrix corresponds to a node in the graph. We write a matrix as an array of numbers enclosed in 2 square brackets. The matrix has 1 row for each node in the graph, and 1 column for each node in the graph. At the intersection of a row and a column, for example, the row corresponding to B and the column corresponding to A, we record the number of edges between those 2 nodes. Since there are 2 edges connecting A and B in the graph, we'll write down the number 2. Let's fill out the first row of the Konigsberg graph's adjacency matrix. There are no edges connecting A to itself, so we'll put a 0 at the intersection of the first row and the first column. There are 2 edges connecting A to B, so we'll put a 2 at the intersection of the first row and the second column. There's also 2 edges connecting A and C, so we'll put a 2 at the intersection of the first row and the third column. Finally, there's 1 edge connecting A to D, so we'll put a 1 in the last column of the first row. As an exercise, you might want to pause the video and see if you can fill out the rest of the adjacency matrix on your own. Then unpause the video and check your work. Got it? Let's see how you did. Let's finish filling out the second row. There aren't any edges connecting B to itself, so we put a 0 in the second row and second column. There are no edges connecting B to C, so we put a 0 in the second row and third column. There is an edge connecting B to D, so we put a 1 in the last column of the second row. The third row corresponds to node C. There are 2 edges connecting C to A, so we'll put a 2 in the first column. There are no edges connecting C to B, so we'll put a 0 in the second column. There aren't any edges connecting C to itself, so we'll put a 0 in the third column. And there's 1 edge connecting C to D, so we'll put a 1 in the last column. There's 1 edge between D and each of the vertices A, B, and C, so we'll put 1s in the first 3 columns. And since D isn't connected to itself, we'll put a 0 in the last column. Now that we know how to construct the adjacency matrix, let's head back to our editor and see if we can write a function that returns the adjacency matrix for a given graph. We're going to write a function that returns the adjacency matrix for a graph. Let's call that function adjacency matrix. The function will have 1 parameter, a graph, and I'll go ahead and give it a docstring. We'll use a Python list to represent the adjacency matrix, and I'll assign it to a variable called adj. Since the adjacency matrix is a 2-dimensional array, each element of this list will be another list representing each row in the adjacency matrix, and we need 1 for each node in the graph. It's going to be really useful to initialize each entry in the matrix with a 0. Let's go ahead and do that by using a nested list comprehension. Now that our adjacency matrix is initialized with zeros, let's loop over each edge of the graph and add values as necessary. The first thing we'll do is extract the two nodes in the edge and assign them to variables called node1 and node2. In order to record this edge in the adjacency matrix, we need to add 1 to the 0 in the row corresponding to node 1 and the column corresponding to node 2. But there might be a problem. If the nodes are integers, ranging from 0 up to 1 less than the number of nodes, then we'll be fine. They correspond to the indices in the adj list of lists. However, if the nodes are strings or integers that aren't in the right range, then we're going to have a problem. Now we could use the Python list index method to get the index of node 1 and node 2 in the graph's node list, but for really big graphs, that's going to be pretty inefficient. Instead, we're just going to assume that the nodes are defined as integers in the range 0 up to 1 less than the number of nodes. Let's document that in our docstring. With that assumption taken care of, we can go ahead and start filling out values in the adjacency matrix. Since node 2 is adjacent to node 1, we need to add a 1 to the 0 in the row corresponding to node 1 and the column corresponding to node 2. And since node 1 is adjacent to node 2, we also need to add a 1 to the 0 in the row corresponding to node 2 and the column corresponding to node 1. When this for loop completes, we'll have a two-dimensional array with zeros in each position where the row node and column node aren't connected by an edge, and the number of edges in each position where the row node and column node are connected by one or more edges. That's exactly the adjacency matrix, so we can go ahead and return adj. Let's go ahead and run the code and see how it works. I'll use interactive mode again to execute the code in the graph.py file to drop into an interactive shell so I can play around with the adjacency matrix function. Let's use the Königsberg graph again so we can check whether or not the adjacency matrix function is working as we expect. We do have a problem though. The way we defined the Königsberg graph before was using strings as nodes with the letters A, B, C, and D. We need to relabel the graph with integers 0, 1, 2, and 3. Let me put that side by side with my editor window so we can use it as a reference while we're building the graph. Let's replace A with 0, B with 1, C with 2, and D with 3. Now we can recreate the graph G so that it uses the integer nodes instead of the string nodes. First, we'll assign to a variable called nodes the range containing the values 0, 1, 2, and 3. Next, we'll assign a list to a variable called edges containing a tuple for each edge in the graph. There are 2 edges between 0 and 1, 2 edges between 0 and 2, 1 edge between 0 and 3, an edge between 1 and 3, and an edge between 2 and 3. Now we can create a new graph using the nodes and edges lists. Now let's pass G to the adjacency matrix function and see what we get. Let's compare that to the adjacency matrix we wrote by hand and see how we did. Excellent. The adjacency matrix function is working beautifully. At this point, we have 3 ways to represent a graph in Python: as a named tuple, as an adjacency list, or as an adjacency matrix. But we've been making an assumption about the kinds of graphs we're using, and it has to do with relationships. Remember, graphs model relationships between objects. We previously talked about the example of a social network, like Facebook. On Facebook, the nodes are Facebook accounts, and an edge exists between nodes if those 2 accounts are friends with each other. If I'm your friend on Facebook, you're also my friend. It's a two-way relationship, but that's not always the case. Consider a social network like Instagram, where accounts follow other accounts. If I follow an account on Instagram, it doesn't necessarily mean that account follows me back. The follow relationship has a direction. We can separate graphs into 2 broad categories: undirected graphs, which are the kinds of graphs we've looked at so far, or directed graphs, which represent directed relationships. The definition for a directed graph is basically the same as the definition for an undirected graph. The difference is an edge in a directed graph indicates a relationship from the node at the start of the edge to the node at the end of the edge, but not the other way around. And when we draw directed graphs, they look pretty much the same as undirected graphs. The difference is we put an arrow on the edge to indicate the direction of the relationship. Let's take a look at how the adjacency list and the adjacency matrix differ for directed versus undirected graphs. In this picture, I've drawn two graphs on 3 vertices with the same edges. On the left-hand side is a directed version of the graph, and on the right-hand side, an undirected version. Let's write out the adjacency list representation of the graph on the right. The first thing we have to do is label our nodes. We'll label them 0, 1, and 2. Node 0 is adjacent to node 1 and node 2. Node 1 is adjacent to nodes 0 and 2, and node 2 is adjacent to nodes 0 and 1. Now let's do the same thing for the directed graph on the left. We'll use the same node labels, 0, 1, and 2, and let's write out the adjacency list representation. In the directed graph, node 0 is adjacent to node 2 because there is an edge with an arrow pointing towards node 2 starting from node 0. However, it is not adjacent to node 1 because the edge starting at node 1 has an arrow pointing towards 0, not starting from 0 and pointing towards 1. So the adjacency list for node 0 contains a single node, node 2. Node 1 is adjacent to node 0 because there's an edge with an arrow starting at node 1 and ending at node 0, and adjacent to node 2 because there's an edge starting from node 1 and pointing towards node 2. Node 2 isn't adjacent to anything because there are no edges coming into node 2 with arrows pointing towards it. So that's a pretty big difference between the adjacency list representation of the directed and undirected graph. Now let's take a look at the adjacency matrix. The first row of the adjacency matrix represents node 0, and so does the first column. Since there's no loop joining 0 to itself, we put a 0 in that position. The second column represents node 1. There is an edge between node 0 and node 1, so we put a 1. The third column represents node 2, and since there's an edge between node 0 and node 2, we put a 1. The second row of the matrix represents node 1. There is an edge between node 1 and node 0, so we put a 1 in the first column. There's no loop joining 1 to itself, so we put a 0 in the second column. There is an edge between node 1 and node 2, so we put a 1 in the third column. The final row represents node 2. There is an edge between node 2 and node 0, so we put a 1 in the first column. There's an edge between node 2 and node 1, so we put a 1 in the second column. But there's no loop connecting 2 to itself, so we put a 0 in the third column. Now let's write the adjacency matrix for the directed version. The first row represents node 0, and so does the first column. There's no loop joining 0 to itself, so we put a 0 in that position. The second column represents node 1. There is no edge between node 0 and node 1 that starts at node 0 with an arrow pointing towards node 1, so we put a 0 in that position. The third column represents node 2, and there is an edge between node 0 and node 2, so we put a 1 in that position. The second row represents node 1. There is an edge connecting node 1 to node 0, so we put a 1 in the first position. There's no edge or no loop connecting 1 to itself, so we put a 0 in that position. And there is an edge connecting 1 to node 2, so we put a 1 in the last position. The third row represents node 2. There's no edge between node 2 and node 0, so we put a 0 in that position. In fact, there's no edges between 2 and any other node in the graph, so we put a 0 in every position in that row. Just like the adjacency list representation, the adjacency matrix representation is pretty different. Let's get back to our code editor and see how we can modify our adjacency dict and adjacency matrix functions to account for directed graphs. The first thing I'll do is remove the graph representation of the Konigsberg graph that we created earlier, just to clean things up. Next, we need to add a field to our graph named tuple that we can use to indicate whether or not a graph is directed. We'll add that to our fields list, and we'll call it isDirected. Now let's take a look at the adjacency dict function and see what we can do to modify it to account for directed or undirected graphs. We don't need to change anything about the first line of the function. We're still creating a dictionary whose keys are nodes and whose values are lists. The change needs to happen inside of the for loop. Let's look at the first line. We take the first component of an edge and assign it to node 1, and the second component of an edge and assign it to node 2. For a directed graph, the edge starts from the first component and ends at the second component. If that's the case, then we still have to append node 2 to the adjacency list for node 1, so nothing needs to change on this line. However, this is where the problem starts. If the graph is directed, node 1 is adjacent to node 2, but node 2 is not adjacent to node 1, so we don't need to append node 1 to node 2's adjacency list. We can skip over this line of code by adding an if statement that checks the value of isDirected and executes this line of code only if isDirected is set to false. And that'll do it for us. Now let's take a look at the adjacency matrix function. It's almost exactly the same. We still need to initialize each entry in the adjacency matrix with 0, loop over all of the edges, and extract the nodes in the edges to two variables called node 1 and node 2. Since this edge starts at node 1 and ends at node 2, node 1 is adjacent to node 2, so we need to keep this line. However, this edge does not imply that node 2 is adjacent to node 1, which means we need to put this line behind an if statement. And there we go. We've modified the adjacency matrix function to work with directed graphs. Just like before, I'll run the code in interactive mode. Let's create a graph with 3 vertices. For the edges, let's add an edge between 1 and 0, between 1 and 2, and between 0 and 2. This is the same as the triangular looking graphs that we saw when we were comparing directed and undirected graphs. Let's put those on the screen so we can compare the output with what we wrote manually. Here's the undirected graph. In order to check our functions against our previous work, we need to set the isDirected field to false. Now let's pass G to the adjacency dict function. Hey, it worked! Just like it should. Node 0 is adjacent to nodes 1 and 2, just like we came up with earlier. Node 1 is adjacent to node 0 and 2, just like it should be. And node 2 is adjacent to nodes 1 and 0, just like it is here. Let's see what happens when we pass G to the adjacency matrix function. Look at that. It matches what we had earlier. Now let's set isDirected to true. When we try to do that, we get an attribute error. It says we can't set an attribute. This is an important property of named tuples that I didn't mention earlier. Just like standard Python tuples, named tuples are immutable. Now you might be wondering, wait a second, but we were able to append an edge to a graph created from this named tuple. What's that all about? Well, that's because edges is a reference to a list, which is a mutable object in Python. So even though G is an immutable object, the objects in G are mutable and can be changed. If that makes your head spin, there's an awesome talk I got to see Al Swigert give at the PyCascades conference a couple years ago. I'll post a link to it down in the description. So since we can't change the value of isDirected, we'll have to create a whole new graph. Let's move this over so we can see the directed version of the graph and see what happens when we pass G to the adjacency dict function. Hey, look at that, it worked. 0 is adjacent to node 2, just like we got earlier. 1 is adjacent to nodes 0 and 2, just like it should be. And 2 is adjacent to nothing. Its value is an empty list. Let's take a look at the adjacency matrix. Would you look at that? It's exactly what it should be. I love it when things work out. You've now seen the precise mathematical definition of both a directed and undirected graph. You learned about adjacency list representation and adjacency matrix representation, and we wrote functions in Python to produce these representations for us. Now you might be wondering, why are there multiple ways to represent a graph? Is there a reason you'd use one over the other? That's a great question. Let's take a look at the answer. We can compare the adjacency list representation and the adjacency matrix representation from different standpoints. For example, one of the benefits of the adjacency list representation is that it can handle arbitrary nodes, so long as those nodes are of a hashable type. On the other hand, the adjacency matrix only works for graphs whose nodes are integers. From the perspective of amount of memory used, an adjacency list typically uses less memory than an adjacency matrix, especially when the graph doesn't have a lot of edges. On the other hand, the adjacency matrix always records data for every edge in the graph. This means that no matter what, you're always using the maximum amount of memory required to represent the graph. For graphs with a large number of edges, this isn't really a problem. But if the graph is sparse, meaning it doesn't have very many edges, the adjacency matrix may not be the greatest choice for a representation. By looking at this comparison, you might be inclined to say, wow, it looks like the adjacency list is usually the best way to represent a graph. And the answer is, it really depends on what problem you're trying to solve. In some cases, the adjacency matrix is the perfect representation. The matrix data structure lends itself to certain kinds of algorithms and certain kinds of operations. Thank you so much for watching all the way to the end of this video. If you enjoyed it, do me a favor, hit the like button and share it with 2 people you think would like it too. And if you haven't already, consider subscribing to my channel. Tap the bell icon to get notified whenever I release a new video. I'm David Amos, and I'll see you in the next video.